Do I have audio? Yep, I've got audio. All right. Check this out. I don't know why. That's Canvas and YouTube.
Yeah, I was just letting you know.
Okay. I appreciate it. What about y'all? Does anybody have any questions from the homework yet? So, no, all right. Let's see here. Got anything to go back to? What's your names? Cody Winland and Jeff Snowden. See what I got for y'all. I know I got labs for you. Cody. Here's your lab from yesterday. And this one.
Well, I always going to drop on the last day of class.
Yeah, I'm not going to replace Jeff. I'm not going to replace any of your grades yet because I don't know which one's going to be below us. You've still got another exam. So.
I'm hoping to make a higher grade on this test, though.
Yeah, all right. Dustin, Devin, Dustin. Lab room yesterday. Is this thing following? There we go. Yeah. Mercer. Ash. Jeff. Emma. Dustin. Garrett. And Garrett. Here you go, Dustin. All right. Now, do either of y'all have any questions from the homework yet? All right. Next week is the last week, and this thing still is not tracking. I guess putting it in my pocket is too much interference for it. So go back to wearing my necklace.
Yeah. On Canvas, but not too much.
You're talking about audio syncing up?
No, with it following.
Oh, well, that's maybe because I've been putting this in my pocket instead of hanging it from the lanyard. I don't know. But I'm not going to try and diagnose the technology. So if it means you miss seeing my smiling face for a couple of seconds, then I'm sorry. Life is hard. Okay, next week is the last week. You got one more exam covering chapters 7 and 11. Here's how it's going to go. I'm going to give you that exam on Monday. You're going to bring it back on Wednesday. There will let's see, your labs are on Thursday. So you don't have a lab last week. Your labs are done. And you don't have any homework for next week. So the 14, 1 and 2, or no, whatever week 14 assignment, that was the last assignment. So Monday, since most of you wait until the weekend to start doing your homework assignment, Monday, come in with questions from the homework assignment, because you will be given the exam, and it will be a take-home exam, and it will be due back on Wednesday, so I can get it graded in time for your grades to be turned in. This chapter 11 is about wave mechanics. We looked at we started chapter 11 last time. We looked at waves in terms of simple harmonic motion. Are not really waves, are they? The simple harmonic motion is sinusoidal, which is why it's called harmonic. But now what we are going to do for the rest of chapter 11 is we're going to transition into how this applies to wave mechanics. What is a wave, first of all? Because this is a fundamental question that.
Fluctuation frequency?
No. This is a fundamental question that physicists, scientists have been trying to address for years, for thousands of years. What is a wave as opposed to what is a particle? Albert Einstein, everybody knows he won the Nobel Prize, but very few people know why. They think he won it because of relativity. He did not. He won his Nobel Prize because of his experiment on the photoelectric effect. Question had plagued scientists since Newton and Galileo. Is light a particle, or is it just a wave? And it was Einstein who said it's both. How would you define a wave? A wave is a mechanism by which energy propagates. Okay? We talked about collisions last chapter. What makes a perfectly elastic collision? Cabe? Oh, I'm asking, is that your name? Okay. Let's see. Pretty sure I got stuff for you. Here's your lab right on top. Hold on, let me see if I've got any more homework for you. You probably know better than me. Do I still have any homework that I haven't given you back? Doesn't look like it. We talked about a perfectly elastic collision being what? A collision in which kinetic energy is conserved. But we also saw that there's no such thing as a perfectly elastic collision, because at the very least, you're going to hear when the two objects collide, when they hit. It's going to make a sound. And any sound is a new form. It's energy any sound produced is kinetic energy that the system possessed before the impact that was converted into sound. That means sound is a form of energy. And that's what waves are. Waves are the mechanism by which it's certainly a mechanism by which energy propagates in this universe. So when you hear sound, what you're hearing are waves of energy compressing and rarefying atmospheric particles, air molecules, and that compression propagates outward like in a spring. So, how much of this is meaningful to you in your various chosen careers and majors? In electronics, well, yeah, obviously there's lots of uses, lots of applications for waves in electronics, telecommunications, printed circuit boards. When every time you establish a current in a conductor, it begins when you apply a potential to the end of a conductor. And that potential propagates like a wave down that conductor at the speed of light. That's why when you get into high-speed digital electronics, all of a sudden, weird things start happening because it takes a finite amount of time for that potential to propagate down that conductor. If it's moving at the speed of light, it takes about a nanosecond for every 8 or 9 inches. That means if you have a signal that's changing faster than a nanosecond, which is what, gigahertz speed? All of a sudden, 8 inches, there's a whole cycle of that wave where you have one potential at one end of a conductor and a different potential at the other end. They're not that conductor is not the same potential over its entire length for that first nanosecond. And because that potential propagates like a wave, when it gets to the other end of that conductor, what's going to happen? It's either going to be absorbed, or transmitted, or it's going to be reflected back to the source, or some combination of the two. When you start working at high speeds, things become not simple real quick. Let's back up to our simple harmonic motion that we started with last time. And as I pointed out, it's motion because it's something that is changing position in time. And it's harmonic because it's sinusoidal. What did simple mean? Who remembers what simple implies? Somebody, anybody? One frequency, exactly. And I also pointed out that it's only simple, it only remains a pure single frequency if it's in a frictionless environment, if there are no losses. Well, in the real world, that doesn't happen. We can get pretty close with a lot of things. That pendulum we were playing with in lab yesterday. I don't know how many of you noticed, but once you set that pendulum going, and especially the simple pendulum, the spring, it kind of damped its own self pretty quick. Took a while, but it did. But that simple pendulum, that would keep swinging for a long time. I don't know if any of you did it, but you could have set it going and never touched it again for the whole second half of that experiment. You could have just kept retiming however many periods you needed over and over again. It was going to keep going. Eventually it would stop and it would end up hanging straight down, but that's going to take a long time. Don't think we're going to deal with any mathematical treatment of this, but I do want you to at least understand the terminology because it will apply. I don't know how much it's going to apply to you. But in radiology, you're definitely going to have to deal with wave mechanics. But I'm not sure how much you're going to deal with damped waves. Y'all are, because you're all going to be dealing with instrumentation and controls, process controls, Who knows what PID stands for? Who can tell me? No? Y'all are electronics folk, right? What's this symbol? You recognize an operational amplifier? Op amp. Why is it called that? Oh, somebody tell me why. You know why it's called an op amp. That's the amp part. What's the op part? Operation. What kind? It's an amplifier that does operations. Mathematical operations. You put that input on your op amp. What do you have? Yeah, you got to put some feedback in here too. What is that? That does a derivative. That is a mathematical derivative or differential amplifier. If you do that, what do you have? That's an integrator. That produces the integral, an integral operation. With these two circuits, you've just mastered calculus. Okay? That is why they're called operational amplifiers, because they perform mathematical operations. Okay, now I'm really going to twist your noggins. Why is it called a transistor? It ain't because it's some guy dressed up like a nun. Why is it called a transistor? Say again? Transition, you're getting close. No. Transfer resistor. It's a resistor that you control how much resistance it has. It's a voltage controlled resistor or a transfer resistor. That's where transistor comes from. It would benefit y'all greatly, all of you, regardless of your major, to learn your vernacular, learn what it means, where it comes from. Anyway, back to PID. Proportional, integral, differential, or derivative. The proportional is just a sum. And I'm sure you recognize this. That's just a summing amplifier. That does addition. And of course, if one of these inputs is negative, what is it when you add a negative? It's a subtraction. Right? Mathematical operations. Why were they invented? And this is more germane than you might think. Op amps were invented because that's how they built computers. The original computers were not digital. They weren't binary. They were analog. They were built for the military so they could do the calculations to launch all that massive artillery over the horizon, over beyond the curvature of the earth. Great distances, and still calculate, all of the forces involved: the gravity, the ballistics trajectory, air resistance, wind resistance, drag, Coriolis effect. All of these things become significant when you start trying to shoot something, 100 miles away, 20 miles away. They had to have computers to do the calculations. Op amps were the basis of those original analog computers. When you do start working in controls, you get that PID. You're going to have a factor that you calculate and plug in for each one of those terms in order to create what's called critical damping. Here's the picture on page 303. You have a sine wave that has decreasing amplitude. That is a damped wave, or damped harmonic motion. Now, figure 1115 shows the difference between underdamped, overdamped, and critically damped. If you're trying to control a temperature or a flow rate, maybe it's blood flow or whatever. If you're underdamped, you're going to come. You're at this is your initial value, and you're looking for this target value. Underdamped is going to come down to that target value or up to it and overshoot and correct, and then it'll be damped until it approaches that target value asymptotically. That is underdamped. If it's overdamped, it's going to end up taking a very long time to come down to that target value. So what you're going to be shooting for is what's called critically damped. The damping that's perfect, that's just dialed right in, so it comes straight down to its target value as quickly as possible without overshoot. That's what chapter 11.5 has to do with what you're going to be working in. 11.6 talks about forced oscillations. You saw how that spring would oscillate at a given frequency whenever you set it to bouncing up and down. That was its natural frequency. When you have any system that tends to oscillate or vibrate, you can force it to oscillate at whatever frequency you want if you add power at that frequency. You've got something on a spring, you can shake it faster. If the spring's stiff enough, you can make it vibrate at whatever frequency you want. But its amplitude, the amplitude of its oscillation is going to be the greatest when you are driving it at its natural frequency. That's what's shown in this figure 1118. That if you drive a system at the frequency it would naturally tend to oscillate at anyway, you're going to get maximum amplitude of oscillation. And in fact, the amplitude that it does oscillate at, when you force it to oscillate at some other frequency, is going to depend on the difference between the frequency you're driving it at and the natural frequency it would tend to oscillate at on its own. Now let's talk about wave motion. How many of you remember a couple of, I'm going to guess months ago now, there was a big hullabaloo because Oh, come on. There was a big hullabaloo because somebody over in CERN, here it is, Giancarlo. Somebody over at CERN said they measured something at greater than the speed of light. Y'all remember when that happened? Because that's not supposed to happen. How can something travel faster than the speed of light? It's not supposed to be able to, but they measured something that did. How do waves propagate? You got a rope laid out on the table. It's the image they use in the book. And you shake that rope back and forth, you create a wave, and that wave will move down the length of that rope. You can, next time you're rolling up an extension cord that's stretched out across the ground, you can whip it and watch that pulse travel down the length of that wave. You can actually do that microscopically and observe it. How fast does that wave go? How fast does it move? Obviously, it depends on a number of factors, the tension in the wire, the force, gravity, etc. The better question I want you to think about is the velocity of that wave the same as the velocity of the particles that make up the wire, the extension cord? Or asked differently, a wave propagating through the ocean, or in your pond, you throw a pebble into the middle of your pond, and the ripples form and they radiate outwards in all directions. Is the speed of the wave the same as the speed of the water molecules that the wave is moving in? The particles of the medium. In this case, water is the medium, or the extension cord is the medium. And it's made up of particles, of atoms, of little chunks of little differential elements of length of wire. Well, the fact is that the wave is moving at a completely different speed than the particles of the medium that it's moving in. When you say something or you make a noise, the sound propagates out at hundreds of miles per hour. What, 800, 750, something like that? Do you think the little molecules of oxygen are actually moving at 750 miles per hour? Not at all. They're not moving very fast, and they're not moving very far. They're just moving a little bit to build up a little pressure, and then that pressure propagates on forward. That's how you can measure something faster than the speed of light. Because information can move as fast as it wants to. Information is massless. The particles that it's actually propagating through, they're constrained to the speed of light or less. Okay? You ever tie a rope to the end of a tree or to a doorknob or something and whip it? What happens? We're going back to those circuit boards now. You take that rope, tie it to the doorknob, and you whip it. That pulse travels down the wave, hits that doorknob, then what happens? It reflects and comes right back at you. And when it gets there, it's gonna jerk your arm back up and down, right? I mean, seriously, have you all done this as kids playing? Ash, have you ever experienced that? You need to add that to the labs because it makes the concept real and physical for you when you feel that pulse come back and hit you. These are the things that happens when waves propagate. When they transfer from one medium into another, how much of the energy gets transferred to the next medium will determine how much is left over to reflect back up where it came from. That's why when you set up antennas and interface circuits together, you always want to match the impedances, so that the energy that gets there, as long as the impedance is matched, the energy that gets there is going to transfer and not reflect back at the source. You hook up an antenna to a radio transmitter and you get the standing wave ratio wrong, and you can fry an amplifier output real quick. There are, who can tell me how many types of waves there are? What are the two, well, let me rephrase that. Who can tell me what the two broad classifications of waves are? Anybody? What was it? You had a guess? Longitudinal and transverse. When you whip that rope and that wave pulse propagates down the rope, is that longitudinal or transverse? That's transverse. The particles of the rope are actually moving orthogonal to the direction of motion of the wave. That's the definition of transverse, when the particles are moving perpendicular to the direction of the wave. Longitudinal is when the particles of the medium are moving in the same direction, or moving parallel to the wave, because they're not moving always in the same direction. They're moving in the same direction and then in the opposite direction. But in both cases, they're moving parallel to the direction of the wave. Who can give me an example of a longitudinal wave? Somebody think of one. Aha! God likes me today. Found it straight away. Told you, when you play with a slinky, you're playing with toys. When I play with a slinky, I'm doing research. Move this. Oh yeah, this is only a mess waiting to happen. Hold that end. Transverse. Send one back. That's a transverse wave. That's longitudinal. Did everyone see it? Y'all come over here. Come sit over here so you can see it. That is a longitudinal wave. Can you see it? That's a transverse wave. Obviously you can see it. All right. Who can think of another example of a longitudinal wave? What happens when you make a sound? Air molecules compress together and then push forward, and they get pushed forward so that they then rarefy, which then drags more molecules in, and it's a successive compression and rarefaction of molecules. That's a longitudinal wave. And waves can be 1 or 2 dimensional, or they can be 3 dimensional. That was a 1-dimensional wave. It's just a very narrow rope. Okay, it moved in 2 dimensions for the transverse. When you throw a stone into a pond, the ripples radiate out in all directions. That's a 2-dimensional wave. It propagates across a plane. Sound is 3-dimensional. When you make a sound, it moves out in all directions equally. When you're reading this material in the book, working the homework problems, you might have to go back and look up some of those formulas for 2- and 3-dimensional. Class isn't over yet, is it? Yeah, it's still on not daylight savings time. And I just completely lost my train of thought. Your fault.
You were talking about homework.
Yeah, you might have to look up, when you're doing the homework and reading through the chapter on this material, you might have to go back and dig out your old trig book or your old algebra book. Look up some of the formulas for the surface area of a sphere or the volume of a sphere. I don't really think there's a whole lot of that in the homework, though, so there'll be time to ask questions about it on Monday before the exam. They're here in section 9, they talk about energy, the energy that's transported by a wave. This is this is where you might have to look up they give you these formulas here. You might have to look up where they get the factors from. We've talked about reflection and transmission of waves. There's one more topic I want to make sure we cover so you will understand something about it. And that's interference patterns of waves. What happens when 2 waves meet? But what happens? It depends. Addition of ordnance. That's ANT, not NCE. Okay. Here's a wave. Here's another wave. What would the sum of these 2 waves look like? How would these 2 waves interfere if they collided? Here you've got 0 and 0. So you've got 0. Here you've got whatever this is, call it 2, And here you've got another 1. So it goes 2 plus the 1 is, or 2 plus 2 more would be 3. So they add together. Here they're 0 and 0 again, so they're back to 0. Here they're minus 2 and minus 2. So the resultant wave between the two of them adding together is simply the sum of both of them at each point. Now, in this case, the amplitude doubles because they're both the same size and they're in phase. What happens if this one's moved over, so this is right here? Like so. Well, now, here you've got minus 2 added to 0. Well, this is going to get real messy real quick. So the sum of the two is minus 2. Here you've got 0 added to 2, so the sum becomes plus 2. Here you've got 0 added to 2, so the sum becomes 2 again. Here you've got 0 added to minus 2, and so it comes down to minus 2 again. And the point is you end up with this. The two waves start canceling out. If this one is moved over 180 degrees, so that it is at plus 2 when this one's at minus 2, then everywhere where this one's at 0, that one's at 0, when this one's at plus 2, this one's at minus 2, they add to 0, and they completely cancel each other out. And yes, I know, I can't draw it and make it that clear. Certainly not after doing it one on top of the other on top of the other. But I do want to try and make that point. So we start with this wave. And we add to it this wave. Well, everywhere they exactly cancel each other out. And the result is a flat line, no wave at all. And it is one of those phenomenon that it may be counterintuitive. You ask, well, where did all of that energy go? Well, it's kind of like, where did all that force go when the object is not being accelerated? When this slinky is sitting here on this tabletop, it's not moving, therefore its acceleration is 0. It's still being subjected to forces. Force of gravity pulling it down, the normal force pushing it up, equal and opposite. Same thing happens here. The energy doesn't go away, but it does cancel. The two energies cancel each other out to produce no net effect, no work. Interference patterns can get very complex. I know you can easily imagine and visualize the next step of a complicated interference pattern. Just picture throwing 2 pebbles into the pond. Both of them create perfect concentric circles of waves radiating outwards. But where they meet, they start creating all manner of complex interference patterns. The same thing holds true with single pulses. And if you look on chapter 11:11, 313, they show you a picture of what happens with 2 waves. In this case, they show a wave coming, a pulse coming this way, moving in this direction, and a second pulse coming this way, moving in that direction. And these pins run out. Moving in that direction. Well, then that shows later, this one has come over here, it's still going that way. This one has over here, and it's still going that way. Question is, what happened when they met in the middle? For that moment, they both went flat. The other example they point out is where you have this pulse and this pulse moving towards each other. And after the collision, you still have those two pulses moving away from each other. But when they met in the middle, they didn't cancel out. They created a spike, a momentary impulse of double the energy. If you've ever looked at, how many of you remember the game Pong? Think about the two balls, two blips on a computer screen bouncing off of the frames. What happens when they hit? It shows them bouncing off of each other. But it only shows that because they add the sound effect. The bink. Okay? Seriously, if you can find the video of this on YouTube, look for it. It's kind of freaky. But because it show you, and they will show you, it will demonstrate. You have that image of the two blips meeting and then bouncing off of each other. When it adds the sound effect, you hear bink, and you see a collision and two blips bouncing off of each other. If they then take away the sound and don't put the bink in there, what you will see is two blips that hit and pass through each other and keep going. The way your brain interprets it will depend on the sound, not what you actually see. Why is that? Relative, think in terms of the stuff we've been discussing in chapter 7 and 11. Why would that be? Because you intrinsically, because it is the sum total of your life experience, you intrinsically equate collisions with sound. Because there's no such thing as a perfectly elastic collision. If you witnessed, and that's what this little video will demonstrate, is if you witnessed a perfectly elastic collision, in your mind it would look like the two objects just passed through each other and never touched. Okay, they'll give you some more examples here of two waves adding. Here's here. Oh yeah, look here on page 314, figure 1139. The case C. That's what I was going to try to draw initially. Is that in fact, if you do go through and you carefully do the addition of ordinates of two waves that are just slightly out of phase with each other, you'll find that you get well, if you want to do it on a spreadsheet or something, do it. You'll see you get a kind of complicated, an interesting event. But what's happening ultimately is the amplitude is decreasing as they get out of phase with each other and till it reaches zero when they're 180 degrees out of phase. And if you keep going, then the amplitude starts growing again. So you get the maximum amplitude at when they're in phase. Does anyone have any questions? Be a really good time to start asking them. Well then, good luck with your homework. Monday, I will give you an exam. You will take it home, and it will be due back in class on Wednesday. No late.
The camera said that we still had another lab.
Nope.
So what day do you want me to come in and do that other lab then?